Third application, electric field at a point due to a charged spherical shell. Charged spherical shell. You consider a charged sphere plus Q, O, radius is capital R. This is positive. Anywhere you consider positive throughout. So direction of electric field is away from positive. Basic principle. Away from positive towards negative. This is positive charge. So away from positive. This portion ds same direction. So phi is equal to closed integral dds. Next step. Here theta is equal to closed integral dds. So phi is equal to E into integral ds is just the surface area of a sphere 4 pi r square. Also, phi is equal to Q by epsilon naught. That is Gauss lemma. Equate this to Q by E into pi RL is equal to Q by epsilon naught. E is equal to Q by 2 pi RL in electric field only we have to calculate. What is Q? 2 pi RL where we got 2 pi RL we don't. E into 4 pi r square only. E into 2 pi RL is for cylinder. Surface area of a cylinder we had 2 pi RL. This is here 4 pi r square. So Q by 4 pi epsilon naught. See, this already we learned. Electric field due to a point charge Q by 4 pi epsilon naught r square. Here we have three cases. This is point on the sphere. Here, point P on the sphere. So you will get capital R square. On the sphere means capital R. No, sir, I want to consider one point here. Draw a Gaussian surface. Here also same concept. P and E, same concept. Theta is equal to 0. So outside means only one change, that is small r. Here to just touching the surface is capital R, but here the outside, what point you are considering, that distance we call it as small r. So for outside point, E is equal to 4 pi r, Q by 4 pi r square. Q by 4 pi epsilon naught. Small r square you are going to get. Same concept only. Only the distance is changed as r. When you consider one point inside, there is no charge inside. Because all the charges lie on the surface, closer to the surface. That is the Gaussian area you are covering. So charge present inside a hollow sphere is zero. Charge is zero means electric field also. So third case here, point inside the sphere, electric field. Simple concept. Now we are going to talk something about capacitance. Capacitance of the conductor. The principle behind that one, you call it as electrostatic induction phenomena. That is, you are considering a charged wire nearby or bringing a spherical conductor. No, sir. Here I have positive charge here. Nearest to your thing, one conductor. This conductor, nearer to this, will have opposite charge. Farther place it becomes. Here, charge plus Q. You are bringing a wire of conductor closer. This is a sphere electrically neutral having equal number of positive and negative charge. But moment you bring closer another charged conductor, you are not touching. Nearby only you are touching. That particular time, the nearer end will become oppositely charged. Same end will become positively charged. When you remove this, these two neutralizers come back to normal. So this is the principle of a capacitor. The two parallel sheets. This is the representation of a capacitor. So the charge given to the conductor is proportional to the potential difference between the ends of the conductor. Q proportional to V, or Q is equal to constant C into V, where C is called the capacitance of the conductor. I can write C is equal to Q by V. Ratio of charge given to the conductor to its potential. C is equal to Q by V, unit of C. What is the unit? Charge by potential, coulomb per volt. Coulomb per volt, another name, farad. 1 farad. Microfarad means 10 power minus 6 farad. Minus 3 millifarad. Correct, Amma? So this is the basic definition of a capacitance. Capacitor is a device used to store charges. That is the aim of the capacitor. Right. Now, parallel plate capacitor. Capacitance of parallel plate or capacitance of a parallel plate. You can write, no problem. Consider two conductors. One is charged with positive. Another conductor you are bringing nearby. You are not touching it, bringing nearby. By electrostatic induction phenomena, just now we saw nearer end negatively charged, farther end the same charge. That one you have grounded. So all the excess positive charge will go to the ground. Distance between the two plates is D. We have to calculate C value. Capacitance we have to calculate C is equal to Q by V. So if we calculate potential V, problem is solved. Okay. How will you calculate? First, positive to negative only electric field direct. Electric field is sigma by epsilon naught. Why? One sheet is positively charged, another is negatively charged. Means we can take this one as electric field due to charged plane sheet. This is charged plane sheet because other side you have grounded. So sigma by epsilon naught. But sigma is nothing but QA by epsilon. The basic formula we wrote, electric field E is equal to QA by epsilon naught. Next, we are going to write the relation between electric field and potential. E is equal to minus dV by dr. That's what we saw in the first topic. Here, there is no question of one positive charge, one negative charge, or two negative charge, two positive charge. So dV by dr, this is called potential gradient. Potential by distance, we call it as potential gradient. So dV is equal to E into dr. Integrate. V is equal to integral. What is E one? QA by epsilon naught. Take it out. Integral dr. Integral dr is nothing but R. Sir, in this case, we have to integrate. We have taken E outside. Integral dr is R you have taken. But what is the limit of integration? 0 to D. Here the distance between the two plates is 0. Here the distance between the two plates is maximum. So that here 0, here I put maximum. Anything you can put. Minimum value to maximum value. So V is equal to E don't substitute. We can substitute later. Take E outside. Integral R is dr is R. 0 to T. So E is. So what is E? QA by epsilon naught. Therefore, capacitance in air medium is Q by V. Q is, let it be, what is V? QA D by epsilon naught Q by V. So QA by epsilon naught. Is this correct? Sigma is equal to Q by A. So I can write epsilon naught. So capacitance of the parallel plate capacitor is C is equal to epsilon naught E by D. Here sigma is Q by A, not Q into A. It's Q by A. So we have to substitute Q by A. Okay. Capacitors in series, capacitors in parallel. 3 capacitors in series connected to external potential C1 plus minus. Generally, positive to negative only current will flow. But here we are going to discuss only charges. Current electricity we have discussed already. Charge by time is equal to Q by T. So current and charge both are directly proportional. Moment you switch on the battery, this capacitor is charged. All the three capacitors are charged. Equal charges. Because same amount of current passing, charge passing per unit time. Charge passing per unit time, we call it as current. So I can say for all the three capacitors, charge is equal. But potential is different. Here, charge Q is constant. Therefore, potential of the first capacitor V is equal to Q by C1. V2 is equal to Q by C2. V3 is Q by C3. Total potential V1 plus V2 plus V3. Take Q outside. 1 by C1 plus 1 by C2 plus 1 by C. Equation. Sir, when you connect all the three capacitors, you will have one resultant capacitance or effective capacitance. That also we have a formula Q by CS. This is the resultant or effective capacitance of the capacitor when connected in series. Compare Q by CS is equal to Q into 1 by C1 plus 1 by C2 plus 1 by C. Cancels. 1 by CS is 1 by C1 plus 1 by C2 plus. Capacitors connected in series is the resultant value. Resultant of the reciprocal of the resultant capacitance when connected in series is the sum of the reciprocal of the individual capacitance. Okay, fine. Next, capacitors in parallel C1, C2, C3. All the three capacitors, starting point is A, ending point is B. So potential difference any 2 points, that is across C1, across C2, across C3. Anything you take, that is always constant. Here, potential V is constant. Therefore, charge Q1 is equal to C1V, Q2 is C2V, Q3 is C3V. You understand? Now, total charge or effective charge when they are connected in series or in parallel. Therefore, total charge is Q1 plus Q2 plus Q3. What is Q1? C1V, Q2, C2V, Q3, C3V. So V common, C1 plus C2. Equation 1. Also, Q is equal to C into V. Basic formula. Q is equal to CV. But this is the resultant or effective capacitance of the conductor when connected in parallel. Individually you have calculated and added. Now, together it will have one value that we are substituting. So Q is equal to Q1 plus Q2 plus Q3. What is the value? C1 plus V2 plus another formula Cp into Cp is equal to C1 plus C2 plus C3. So the resultant capacitance when they are connected in parallel, the sum of the individual capacitors. We can use a small value and we can prove what is the resultant capacitance, or we can find in series, in parallel, what is the resultant for three capacitors C1, C2, C3, 1 microfarad, 2 microfarad, 3 microfarad. Calculate the resultant capacitance when they are connected in series and when they are connected in parallel. That is the question. Cp C1 plus C2 plus C3, 1 plus 2 plus 3 microfarad. In series, this is in parallel. In series, 1 by Cs is equal to 1 by 1 plus 1 by 2 plus 1 by 3. 1, 2, 3, common value, LCM, 6. So, 6 plus 3 plus 11 by 6. Most of the students, what they will write, 1 by Cs is equal to 11 by 6 microfarad, they will write. That is the wrong value. Because this is the reciprocal of the resultant. We want only the resultant. Therefore, Cs is equal to 6 by 11 microfarad. 6 by 11. You can cross check your answer with a small thing in mind. The resultant here is less than 1 microfarad. You see your problem. Minimum value is 1 microfarad, but you are getting the resultant less than 1. So, in series connection, the resultant capacitance value will be lesser than the least. Out of the 3, least is 1. That also we are not getting. Lesser than the least. No, sir. Parallel only I will write. No, no. Cp, what is the value? We got 6 microfarad. The resultant 6 microfarad is greater than the greatest. Out of the 3 values, it is the greatest value here. 3 microfarad. Your answer 6 microfarad is greater than the greatest. Okay, so this is capacitance of the conductor. So we saw what is electric flux and what is Gauss law with proof. We saw 3 applications of Gauss law. Electric field due to charged wire, due to charged plane sheet, 2 plane sheets. Then we have discussed about the principle of a capacitor, what is called a parallel plate capacitor. Basic values of the resultant in the case of capacitors connected in series and parallel. These are the topics we have done today. We'll continue. Thank you.